Hi everyone, and welcome to this video in a series that I'm doing about functional analysis on this theorem called the Krein-Milman Theorem, which holds in slightly more generality than some of the objects that we've been looking at or some of the results hitherto considered, but is extremely important in its own right and concerns in some sense, the geometry of a lot of these algebraic spaces that we've been considering so far. In particular, this is going to hold in locally convex topological vector spaces, which in contrast to things like Banach or Hilbert spaces, are not necessarily normed vector spaces. They're not normable. That is to say, there might not exist a norm which gives rise to the topology, and in that sense, they're more general because a Banach space is a complete normed vector space, and then a Hilbert space is a Banach space for which the norm arises from an inner product, and so on. Intermediate between Banach spaces and these LCTVSs, so to speak, are these Fréchet spaces where the topology is generated by a countable family of seminorms, and this is even more general than that. So let me write down some definitions before I get into the content of the theorem. So x comma tau, where this is going to denote a topological space, is a locally convex topological vector space. Actually, let me just do a topological vector space first. Is a topological vector space if, of course, x is a vector space and tau is some topology on X such that we often demand the following technical considerations. Well, one is sort of obvious for it to be compatible to vector space axioms, that the vector space axioms, or operations, I should say, are continuous with respect to tau. So just like the way we define topological groups, for example, that is to say addition and scalar multiplication. So the vector space operations are continuous with respect to tau. And moreover, this is the technical point that we like to make. Every point or every singleton set containing a point is a closed set. And these in particular imply that when we talk about a topological vector space, we implicitly assume that they're Hausdorff to avoid any kinds of pathologies. So thus X is Hausdorff, that is to say you can separate points by open sets. And this kind of, this is done for cleanliness, though we don't have to repeat hypotheses or we don't have to keep saying Hausdorff. We can just assume that all topological vector spaces are of this form because most of the ones that arise in nature are going to be Hausdorff anyway. So this is like the assumption in, for example, sometimes in non-algebraic geometry contexts, you assume that compact means compact and Hausdorff, and it's only with weird pathological topologies with poor separation properties like the Zariski topology that you don't impose this condition. So you have things like quasi-compact, which, again, conventions vary, but this is what we're going to use. And for the rest of this video, I'm also going to assume that X is a real vector space because this makes the geometry easier, and this is the setting in which the Krein-Milman theorem holds. So I'm going to give some definitions. So let X be a real vector space. So not necessarily a topological vector space quite yet, because we can define this next thing in greater generality. And we're going to let S be a subset of X. Then we define the convex hull to coincide with what morally makes sense in Euclidean space. So in Rn, we just take convex linear combinations, and that's exactly what we do in the general setting. So we take all linear combinations of the form lambda I xi, where I is equal to 1 to whatever the dimension is, let's say it's n-dimensional. And, or actually, no, this is not contingent on dimension. What am I saying? So n is going to be a natural number, as long as we have any affine linear combination of this sort. So xi are going to be an S, and we want this to be a convex linear combination, which is to say that the lambda I, these constants, are going to add up to 1 in this span. Great, so this is the convex hull of S. And at least in Euclidean space, where it's easy to visualize, we can imagine taking a bunch of points and then like wrapping, the analogy that I've heard someone use is like wrapping like cling film or like some kind of foil around them and then pulling. It's like this minimal set that you can get, so the word hull is justified. And it's what you get when you fill in all the lines that you can possibly achieve. That is to say, you create a line segment, so this affine linear combination where you start at one point and then you kind of parameterize this with an interval, so you have like 1 minus t times the first point plus t times the second point, and then you eventually reach the second point as t goes to 1. So it's not necessarily true that the convex hull is a closed set, and because of this, we're also going to define this notation. So conv bar of S, let me just write for completeness sake, the convex hull of S is this, and then the closure of conv S is the closed convex hull. Okay, so the Krein-Milman theorem is a fairly general result about compact and convex subsets of a locally convex topological vector space. And one last definition, or maybe two and one, we have to define these things called extremal points and faces. So again, we're going to let X be a real vector space, and K is going to be nonempty convex subset. Then a subset of K, let's call it F, is called a face of K if it is well, I guess non-empty I have to specify. It's also convex, so like K, it's a convex subset of a convex set. And the following technical point holds. If we have for 2 points x0 and x1 in K, and any lambda in strictly between 0 and 1, so in this open interval, 1 minus lambda x0 plus lambda x1 lies in F. So if this any point on the line connecting them lies in F, then in fact the endpoints lie in F. So x0 and x1 themselves lie in F. So this is what it means to be a face. And a point in the exact same setup as above, so K is non-empty convex subset of some real vector space, is called an extremal point, or just extremal, if this has a quite similar condition, so x0, x1 in K, and for lambda between 0 and 1, if we have that this affine linear combination, 1 minus lambda x naught plus lambda x1 equals x, then in fact the endpoints coincide with x, so that x naught equals x1 equals x. And how can we translate this condition? Well, a point in some non-empty convex subset is going to be an extremal point if and only if the singleton set, let me write this as a little remark below. Let's note that this holds true. X is an extremal point if and only if the set which is equal to the singleton consisting of X is itself a face of K. Or equivalently, there's no open line segments in K containing X. And there's this nice diagram, I think in the book of Buehler and Salomon, where even the Wikipedia entry has a nice visual of this. So you can look at that to get some intuition about extremal points and faces. And now with this notation above, we're going to let squiggly e of x denote the extremal points, so the set of all x and k, such that x is I'll hyphenate k extremal to condense because I'm lazy. And now we are, I think, in a position to state and prove the Krein-Milman theorem. So this theorem, again, it's quite remarkable that such a theorem holds in this kind of generality, because then we can apply this to certain special situations like not just Banach and Hilbert spaces, which of course it holds true, but for duals of Banach spaces, for other sorts of functional analytic spaces, and in conjunction with other theorem like the Banach-Halaoglu theorem, which states that the closed unit ball in the dual of Banach space, or in fact any normed vector space, is compact in the weak star topology, allows us to show that there exists an ergodic measure for any homomorphism of a compact metric space, which is quite a neat theorem. And then this result, the Krein-Milman theorem about extremal points, we can characterize ergodic measures that in such a situation, ergodic measures are exactly those that are the extremal points of all invariant measures, which form a convex set for a compact metric space. So again, these are really pretty applications to ergodic theory. And when I upload my series, after I TA for the course and learn all of that material properly, then I'll include that application. So just to give you a sense of how powerful this theorem is and why it's so interesting in its own right. And now let's state this theorem. So let X be a locally compact topological vector space, so an LCTVS, and K and X a non-empty compact convex set then I'm going to write this succinctly and speak more out loud. K is the closed convex hull of its extremal points. Now, in any setting with less abstraction than this one, this would be an obvious assertion because you can just visualize this. Like you have the extremal points, these lie kind of at the ends of your compact convex set. Compactness means that it's contained in some sense, so you can basically identify these. And these should always exist heuristically. And if you take the convex hull, so you do this like cling film trick and you form the closure, because of compactness, of course, we're working in a Hausdorff setting, so every compact set is closed, then it should be intuitively plausible that this compact convex set is equal to the closure of the convex hull of its extremal points. However, the fact that this holds in a situation as general as an LCTVS is quite remarkable, because we know that even for quite controlled situations like Banach spaces where we have a decent sense of bounded operators and we have amazing theorems that, for example, the bare category theorem affords us, like open mapping, closed graph, uniform boundedness even, and Han Banach supplies us with this amazing supply of linear functionals in the space, so we have a really good sense of the convexity, the duality, and the completeness properties of a Banach space. A lot of its geometry still remains fairly shrouded, and the operators on a Banach space in general admit some complicated descriptions compared to those for like a Hilbert space, which is very well understood. So the fact that this holds not just for Banach spaces, but for things even more general than Fréchet spaces, for LCTVSs, is fairly remarkable that our intuition still holds true, and that we can get this nice geometric characterization of extremal points of faces of compact convex sets in the locally convex setting. So this is the real power of the assumption being locally convex, because if we relinquish that, this theorem, of course, fails spectacularly, and there's no interesting structure to the algebraic objects we're looking at. So anyway, enough kind of talking out loud, and now we're going to get to the proof of this theorem, which is 5 steps. And it will consist of an interesting Zorn's lemma argument, and as far as I know, there's no way to evade this, so this is at least dependent, or at least reliant on the axiom of dependent choice, and I don't think there's any funny business like that one weird proof of uniform boundedness where you can just kind of, like, anyway, there's this one 5-line proof which doesn't use choice at all, and it's got this really cheeky title, a really simple, straightforward proof of the uniform boundedness theorem, which in fact Banach and I don't remember who it was who originally came up with this proof, maybe Dieudonné, that would make sense, in 1922, 5 years before the modern proof, the 1927 proof, used this technique called the gliding hump technique, and this did not rely on any form of choice. So it's independent of choice, or I mean, it can be proved in ZF, but anyway, enough about the set theoretic implications of these things, which is interesting for other reasons. Let's start with step 1. So first I'm going to define script dk, which is going to consist of the non-empty compact convex sets. Oh, wait. These subsets of X that we're interested in, and we're going to define a partial order on K via F is bounded above in this partial order by K if and only if definitionally F is a face of K. And it's not hard to see that this does in fact afford a partial order on K, that transitivity is very easily verified, for example, and I'll leave it to you to think through the other axioms. Then, as I've just stated in words, K under this relation that we've just defined is a poset, a partially ordered set. And the real substance of step 1 is the claim that every nonempty chain C has an infimum, has a greatest lower bound with respect to the partial order just defined. So the proof of this is that, of course, every element is closed because K is compact and X is Hausdorff. And of course, anyone with a kindergarten education knows that a compact subset of a Hausdorff space is closed. And this implies that every nonempty chain has an infimum by taking C0 to be the intersection over all elements in the chain, and this is kind of like reverse to how we use Zorn's lemma to prove that every commutative ring is a maximal ideal. Instead of taking a union of chains which are formed by inclusion, in this case we take an intersection because we know that intersections of these closed subsets are going to be closed. And so this is valid because then this intersection remains within K, and C0 in particular remains within this chain. So this proves step 1, and we've shown that everything has an infimum, so we can already see how we're gearing up to use Zorn's lemma. So now let's proceed to step 2, which invokes the continuous dual. So let K be an element of fancy K, that is to say it's non-empty, compact, and convex, and L be an element of the continuous dual, that is L from X to R is a continuous linear functional, then there are two assertions that can be made. So let's denote by F the intersection of K with the pre-image of the supremum of L over all k. And then the first assertion is that this is compact and convex, and moreover, f is not just arbitrarily defined with respect to k as above, but if we define it in this way, then f is in fact a face of k. Okay, so this is an alarmingly easy argument. When I first went through this proof, I thought it would be much longer because it could get quite involved, especially with the second step. But first, let's show. Let me denote this 1, 2 Roman numeral respectively. Let's show the first part, which is that let's C denote the supremum. And since K is compact, L is continuous, then at least we know that the set F, K intersect L inverse C is non-empty, so that proves one thing. And moreover, with more point set pacts, so K is closed, and using continuity of L again implies that F is closed, being the preimage of this closed set intersect with this other closed set K. So F is a closed subset of a compact set, and this of course implies that F is itself compact. Standard fact. And finally, this is going to rely on some facts about convexity, which I'm going to assume that you're familiar with, but the proof is not so hard if you want to try to do this on your own. Since K is convex and L is, in particular, a linear map, then F is convex. So this heuristic that linearity preserves convexity. And we've shown the three things that we wanted to in part one, which is to say that it's non-empty, it's closed, and it's, well, closed implies convex, closed implies compact in this case, and then separately, F is convex. So this implies that F is in K. And as for the second part, now that we've shown this first part, we can ask the question, is F a face of K? This is a well-defined question to ask. And you just kind of follow your nose for this. Like, you fix two elements, x0, x1, in K, and a real number lambda between 0 and 1. You just kind of brute force check the definition. Such that, actually, brute force plus this one clever construction. So you're going to let x be equal to 1 minus lambda x0 plus lambda x1. You're going to choose lambda such that this linear combination lies in F. Okay, so then the cleverness comes here. So 1 minus lambda L of x0 plus lambda times L of x1 is equal to L of x. By definition, you just use linearity, and then this is equal to C. And this implies that 1 minus lambda C minus L of x0 plus lambda, let me do this in another line, c minus lambda of x1 is equal to 0. Great. And now, since c was taken to be the supremum, we know that c minus both L of x naught and minus L of x1, certainly these are non-negative. They're 0 at best if the supremum is achieved at either x0 or x1. And this implies that L of x0, combining this with the previous fact, equals L of x1, which is in fact equal to c. So the supremum is achieved at both endpoints, and this proves that both x0 and x1 lie in F, because that is how lambda was chosen. And because of this, we've shown that from x0 and x1 and k, with this condition holding, this point on the line segment belongs to F, then in fact the endpoints belong to F implies that F is a face. So this proves step 2. Okay, wonderful. Now there is step 3. Which is to show that every minimal element of K is a singleton set. Okay. What's the proof of this? So we're going to fix a non-singleton set, K, and we're going to choose 2 points x0 and x1 in said non-singleton element, such that x0 is not equal to x1, and we can do this because K is not a singleton. So there's more than one point. And here's where we use the assumption on X globally now. And this is in fact the only, no, there's one more place, but this is the substantial place. Since X is an LCTVS, we can prove by Han-Banach basically this, I should have actually included this earlier, that's my bad, because this is non-trivial, but you can see how this follows by separation of convex sets. So this is not super hard to believe in principle, but rigorously showing it, I might do that in a separate video. Anyway, one property of locally compact topological vector spaces is that, well, first of all, let me show something that follows from the definition. There's a convex open set. Let me call it U. That contains one of the points and not the others without loss of generality. Let's say x1 is in U, but x0 is not. And theorem, which will sadly go proofless in this video, there exists a continuous linear functional L such that it achieves its minimum at this prescribed point x0. You can basically separate a point and a convex set by choosing a linear functional that achieves a smaller value at x0 than it does uniformly throughout an open set that is disjoint from it. So such that L of x naught is less than L of x for all x in U. And this in particular implies that said linear functional satisfies. And it certainly is not guaranteed to be unique or anything of the sort. There might be an ample supply of such linear functionals which do this. This implies that in particular L of x naught is less than L of x1. And now we can use this specific linear functional, L, in the manner that step 2 suggests that we should use it, which is to say we can construct this face F, which is equal to the preimage of the supremum of L over all k intersect with k, supremum of k lambda, sorry, L, and this is a face of k such that x naught lies in k, but outside of this face F. So this is by construction. And this all goes to show that k as initially chosen, which has 2 distinct points at least, that is to say it's not a singleton, cannot be minimal because we have found this face. So that has to be necessarily bounding k below. Hence we have a non-trivial element which bounds it below. That is to say, well, F is a face, it's non-empty. So F is less than or equal to k, and k is not minimal. And since the only assumption on k was that it had more than one point, then this shows that all singletons have to be, or all minimal elements of k have to be minimal. That concludes step 3. So let's summarize so far what we've done. In part 1, we've shown that every nonempty chain has an infimum. We've done this with basic points of topology facts. In step 2, we've used these facts about linear functionals and found this way of supplying faces, which we used in the following step, that is step 3, to show that every minimal element of k is a singleton. And now step 4 uses step 3 and Zorn's lemma to show that the extremal points of k are non-empty. And then later we can conclude, almost immediately in fact, that as soon as the extremal points are non-empty, that is to say there's at least one, then any compact convex non-empty set is the closed convex hull of its extremal points. It's the content of Krein-Milman. So step 4, for any for any compact convex non-empty set K, the set of its extremal points is non-zero. So proof, this is like almost a one-liner using the preceding steps. So by step 1, and by Zorn's lemma, we've shown that every chain can be bounded below. So by Zorn's lemma, there exists a minimal element in K. Let's call this E. Such that E is less than or equal to K. And by step 3, since E is minimal, E has to be a singleton. And because of this relation, E is less than or equal to K, and E is a singleton, that is to say, X is a face of E. Sorry, X is a face of K, what am I saying? A singleton is a face if and only if it's an extremal point. That is to say, X is an extremal point. So we have non-constructively found the existence of some extremal point. In fact, there are sort of two black boxes here. One is, of course, the axiom of choice / Zorn-Zillmer, and the second is that we know that there's some singleton which this is equal to, but there's no way to really find this. So this is, of course, a long kind of winding road with no hope of finding the singleton explicitly. So given a compact-convex set, there's really no knowing without any additional extremely obvious structure on it what the extreme points are, but we know that at least one exists. So this shows that the extremal points are non-empty, and this concludes the penultimate step. All right, and now step 5, which is to prove the theorem. Let K be non-empty, compact, and convex. Then it is the closed convex hull of its extremal points, which we know by step 4 to be non-empty. So this is not a silly thing to say. So proof of this. Of course, by definition, the extremal points are going to lie in K, and as is their closed convex hull. So we know that at least one inclusion always holds. And the real upshot of this theorem is, of course, proving the other inclusion. So it's surprising that K is included in and therefore equal to the closed convex hull of its extremal points. So for the reverse inclusion, assume, for the sake of contradiction, that there exists an element and their difference that there exists a point X that is in K but is not in conv bar of E of K and now since X is an LCTVS, there is an open convex set, let's call it V, so that we distinguish it from the previous open convex set used in step 3. Such that X lies in V, and such that the intersection of V with the closed convex hull is non-trivial. Okay, so now, since by step 4, E of K is non-empty. Oh, wait, sorry. Oh, no, I misunderstood. The intersection of V with the convex hull is disjoint. So V is disjoint from this closed convex hull. We can, oh wait, of course this is true. We can find a convex set that separates X from, that includes X but separates from X from the closed convex hull. So we can always do this. because we are working in a locally convex space. And it follows from the same theorem that I invoked above, which I really should have proven before this. There exists a continuous linear functional, so some L in x star, such that L of x is greater than, so we can use the linear functional to separate it from everything now in the convex hull because they're disjoint. Of E of k of L. But now by step 2, the set F equals K intersect L inverse of the supremum over all compacts. Over everything in K. Over all points in K of L is a face of K. And for this reason, all of its elements are going to lie well, we have the intersection of this face. Let me think for a second. Wait, I have to remember how this goes. Oh yes, okay, so F is going to be disjoint from the extremal points. Yeah, this has to be right. So F is disjoint from E of K. And this follows from, of course, this is the whole point of setting up that specific linear functional. And now we use, I think, basically the one step that we have not used so far, which is step 3, which is that F has an extremal point. So F extremal point x naught, but x naught would be an extremal point of K by transitivity, because an extremal point of a face is of course going to be extremal for the original compact convex set. This would be in E of K, but this contradicts. Let me just say which contradicts. Which contradicts. Sorry, which. The fact that F is disjoint from the extremal points of K. And this proves the Krein-Milman theorem. Great. And yeah, so we can see how we've gone through this whole process. Compactness was the needed technical assumption so that we can make these points-set arguments in step 1 especially. And in, really step 1 is the foundation. And then we used this theorem about using linear functionals in locally compact topological vector spaces to separate these things so they take on either greater or lesser values than some disjoint open set, which is convex. These always exist. Then we proved that every minimal element is a singleton with this sort of technique. And finally, using the fact that every minimal element of the set of, or I guess I should, not to get into set theory, I'll just be loose with my language, the set of compact convex non-empty subsets of X is a singleton proves that the extremal points are non-empty, always. Well, I have grossly miswritten that. That should say E of k is not empty. And finally, once we know that the extremal points are non-empty, we can use some more technical arguments to, again, use the separation, supply linear functional, and then argue by contradiction that it has to be equal to, or any element of k has to be equal to the convex hull, the closure of the convex hull of its extremal points. This is in fact the content of the Krein-Milman theorem, and we are done. So thank you for watching this, and in some coming videos, I'll probably look at some applications in ergodic theory, as well as how we can combine this with other existing theorems in, let's say, more restricted settings, like, for example, with normable vector spaces, this allows us to apply Banach-Haloglu, and in Banach spaces specifically, where we can look at things like convex subsets. So again, thanks for watching, and hopefully I'll see you in future videos in this functional analysis series.